Welcome! In this session, we'll explore LeetCode problem number 305, number of islands 2. This problem challenges us to dynamically calculate the number of islands in a grid as land cells are added incrementally. Let's dive in and solve this step by step. In this problem, we are given a 2D grid with dimensions m by n, where every cell initially represents water, denoted by the value 0. The task is to incrementally add land, represented as 1, at specific positions provided in an array called positions. An island is defined as a group of adjacent ones that are connected either horizontally or vertically. After each addition of land, we need to determine the total number of islands in the grid and return these counts as a list of integers. The positions where land is added are given as row and column coordinates, and the output reflects the number of islands after each addition. The grid starts completely empty, and the challenge is to efficiently track how the number of islands evolves as land cells are added. Let's take a closer look at an example to understand the problem. Here, we have a grid with 3 rows and 3 columns. The positions where land is added are specified as 0, 0, 0, 1, 1, 2, 2, 1, 1, 1. Initially, the grid contains only water, so all cells have a value of 0. As we go through the positions, we will add land one at a time and calculate the number of islands after each addition. The output for this input is 1, 1, 2, 3, 1, which means that after each land addition, the number of islands changes according to these values. Let's explore how this result is derived step by step. First, we add land at position 0, 0. This creates a single island since there is one piece of land surrounded by water. The grid now looks like this: 1 in the top left corner, with the rest of the cells still 0. The number of islands is 1. Next, we add land at position 0, 1. This new land connects horizontally to the existing land at 0, 0, so it becomes part of the same island. The grid now has a horizontal strip of land in the top row, but the total number of islands remains 1. Then, we add land at position 1, 2. Since this piece of land is isolated and not connected to any other land, it creates a new island. The total number of islands increases to 2. Now, we add land at position 2, 1. This is another isolated piece of land, so it forms a third island. The grid now contains 3 separate islands, 1 in the top left, 1 in the middle right, and 1 in the bottom center. Finally, we add land at position 1, 1. This piece of land connects all 3 existing islands into a single larger island. The grid is now fully connected, with all land cells forming one continuous island. As a result, the number of islands decreases from 3 back to 1. This step-by-step process explains why the output for this example is 1, 1, 2, 3, 1. In another example, we have the simplest possible grid, with just 1 row and 1 column. The positions array specifies that land is added at 0, 0 twice. Initially, the grid is empty, represented as a single cell with the value 0. After the first addition of land at 0, 0, the grid contains 1 land cell, forming a single island. Adding land at the same position again has no effect because the cell is already land. Therefore, the number of islands remains 1 for both additions, and the output is 1, 1. This highlights an important property of the problem: adding land to the same position multiple times does not create additional islands. There are several constraints and edge cases to consider for this problem. The grid can be very large, with up to 10,000 rows and columns, and the positions array can contain up to 10,000 additions. Each position is guaranteed to be within bounds, but adding land to the same position multiple times should not increase the island count. Edge cases include scenarios like sparse additions, where the positions are far apart and result in many small, disconnected islands, or dense additions, where positions are close together and cause frequent merging of islands. Special cases like grids with only 1 row or 1 column should also be handled carefully, as well as large grids with very few land additions. These considerations are critical for designing an efficient solution. To solve the problem of counting the number of islands in a dynamic grid where land cells are added incrementally, we need a strategy that efficiently handles dynamic connectivity. The first approach to consider is the brute force method. The intuition here is straightforward: after each land cell is added, traverse the entire grid using either BFS or DFS to count the number of connected components, which represent islands. While this method is simple to implement, it has significant computational overhead. Each traversal of the grid takes m*n time, and since this traversal is repeated for every land addition, the total complexity becomes k*m*n, where k is the number of additions. This makes the approach highly inefficient for large grids or numerous additions, as it recalculates redundant information repeatedly. While simple, this approach is impractical for scenarios requiring high scalability. To address the inefficiencies of the brute force method, we can use a union-find data structure, also known as disjoint set union, to dynamically track connected components. The idea is to treat each cell as a node and use union-find operations to manage connectivity. Initially, all cells are water, meaning no nodes are connected. When a new land cell is added, it is marked as land and treated as a new node. We then check its neighbors. If any of them are part of existing islands, we unify them into a single connected component. This approach ensures that the number of islands corresponds to the total number of connected components tracked by union find. The efficiency of this method comes from the optimizations in union find, such as path compression and union by rank, which allow union and find operations to run in nearly constant time. As a result, the total complexity is k*alpha m*n, where alpha is the inverse Ackermann function, a very small value. This makes the approach highly efficient and scalable. While it requires maintaining additional data structures like parent and rank arrays, the trade-off is well worth the significant performance improvement over brute force. Another option is to use a flood-fill approach with lazy updates, which is a variant of the brute force method. Instead of traversing the entire grid after each land addition, we focus only on the regions directly affected by the new cell. Using BFS or DFS, we explore the neighboring cells to determine if the new land cell connects to any existing islands. This localized updating reduces the scope of computation compared to the brute force method. However, the worst-case complexity remains k*m*n, particularly for dense grids where many land cells are added. While this approach can sometimes perform better than brute force, especially for sparse grids, it still lacks the guaranteed efficiency of union find. The absence of optimizations like path compression means it cannot achieve the near-constant time updates that make union find so powerful. The chosen strategy for this problem is the union find approach, as it offers the most efficient solution for dynamically tracking connected components in a grid. One of the key insights supporting this choice is that each land addition impacts only a small portion of the grid, making union find's localized updates extremely effective. Additionally, union find is specifically designed for problems involving dynamic connectivity, making it a natural fit for this scenario. Its scalability is another major advantage, with near-constant time operations enabling it to handle large grids and numerous additions efficiently. While it does require additional data structures like parent and rank arrays, these are a manageable trade-off for the significant reduction in redundant computations. In contrast, brute force methods, while simple, are computationally prohibitive for large inputs, and flood-fill approaches, though slightly optimized, lack the guaranteed performance of union find. By leveraging optimizations such as path compression and union by rank, the union find strategy provides a robust and scalable solution to the problem of counting islands in a dynamic grid. To start, the problem number of islands 2 asks us to dynamically add land cells to a grid and determine the number of islands after each addition. An island is defined as a group of connected land cells, either horizontally or vertically. Initially, the grid contains only water, and our challenge is to efficiently update the count of islands as land cells are added one by one. A brute force approach, where we recalculate the number of islands from scratch after each addition, is computationally expensive and impractical for large grids. Instead, we use a union-find data structure, also known as disjoint set union, to manage dynamic connectivity efficiently. The algorithm starts with an initialization step where we define the grid size, set up the union-find structure, and initialize all cells as water. This involves creating a parent array to track the representative of each node, a rank array to optimize unions, and a count variable to keep track of the total number of islands. Initially, the grid contains no land, so the island count is 0. Now, for each land addition, we extract the coordinates of the cell being converted to land and convert these 2D coordinates into a 1D index. This simplifies the union find operations since we can treat each cell as a node in a flat array. If the cell is already land, we simply skip it, as it won't affect the island count. Otherwise, we mark the cell as land in the grid and increase the island count by 1, as a new land cell initially forms its own isolated island. Next, we examine the 4 neighboring cells, up, down, left, and right. If a neighbor is within the grid bounds and is already land, we use the union find operation to check whether the current cell and the neighbor belong to the same island. If they do not, we merge their islands using the union operation and decrement the island count, since 2 islands are merging into 1. After processing all neighbors, we append the current island count to the result list. After processing all land additions, we return the result list, which contains the island count at each step. The key insight here is the efficiency of the union find data structure. Its operations find, union, and path compression are extremely fast, with a time complexity of O, alpha, n, where alpha is the inverse Ackermann function, which grows extremely slowly. This ensures that even for large grids, operations remain efficient. Additionally, the concept of dynamic connectivity is fundamental here. Each cell in the grid is treated as a node, and as land is added, we dynamically connect nodes to form larger components. The count variable allows us to efficiently keep track of the number of connected components, or islands, as the grid evolves. Let's take a closer look at the data structures used in this algorithm. The union find structure consists of 3 main components: the parent array, which tracks the parent node of each cell and helps identify connected components; the rank array, which ensures that union operations attach smaller trees under larger ones to keep the structure balanced; and the count variable, which keeps track of the total number of connected components in the grid. Additionally, we use the grid itself to track which cells are water and which are land. In terms of complexity, each land addition involves up to 4 find operations and potentially 1 union operation, all of which run in O, alpha, n, time. For k land additions, the total time complexity is O, k asterisk alpha, n. The space complexity is O, m asterisk n, as the union find structure must store data for all cells in the grid. Let's walk through an example to see the algorithm in action. Consider a 3x3 grid, and we're given the positions 0, 0, 0, 1, 1, 2, 2, 1, 1, 1. First, we add 0, 0. We mark this cell as land and increment the count to 1. Since there are no land neighbors, the result is 1. Next, we add 0, 1. Again, we mark it as land and increase the count to 2. However, the neighbor 0, 0 is already land, so we union these 2 cells, reducing the count to 1. The result so far is 1, 1. Then, we add 1, 2. We mark it as land and increment the count to 2. Since it has no land neighbors, the result becomes 1, 1, 2. Next, we add 2, 1. Marking it as land increases the count to 3. With no land neighbors, the result becomes 1, 1, 2, 3. Finally, we add 1, 1, marking it as land and incrementing the count to 4. This cell has multiple land neighbors 0, 1, 2, 1, and 1, 2. We perform union operations to merge these islands, reducing the count by 1 for each merge, ultimately bringing it down to 1. The final result is 1, 1, 2, 3, 1. This step-by-step process demonstrates how the algorithm efficiently updates the island count after each addition, leveraging the union find data structure to handle dynamic connectivity with minimal overhead. Here, we start with the definition of the numberIslands2 function, which takes the grid dimensions m and n, along with a list of positions where land is being added. Inside the function, we have the findHelper method, which implements path compression to efficiently locate the root of a given node in the union find data structure. This optimization ensures that future lookups are faster by flattening the structure. Next, we define the union method, which merges 2 disjoint sets by linking their roots. It uses union by rank to maintain a balanced structure, where the smaller tree is attached under the larger tree. If both trees have the same rank, one root is arbitrarily chosen, and its rank is increment. Then, we initialize 2 arrays, roots, which tracks the parent of each cell, and ranks, which stores the rank of each root. Both are sized to accommodate all cells in the grid, with roots initially set to -1 to signify water. The variable count is initialized to 0 to track the number of islands, and result is an empty list that will store the island counts after each operation. Finally, we loop through each position in positions. For each x, y pair, we calculate its corresponding index in the flattened grid. If the cell is already marked as land in the roots array, we simply append the current count to the result and skip further processing for this position. If the cell is not already land, we mark it as land by setting roots index to its own index. This essentially makes the cell its own root. We then increment the island count, as this new land initially forms its own island. To check for potential merges with neighboring islands, we iterate over all 4 possible directions: right, down, left, and up. For each direction, we calculate the neighbor's coordinates, NX, New York, and its corresponding index in the grid. If the neighbor is within bounds and is already marked as land in the roots array, we check if the current cell and the neighbor belong to the same island. If they do not, we use the union function to merge the 2 islands, and decrement the island count because 2 separate islands have become one. After processing all neighbors, the updated island count is appended to the result list. Once all positions have been processed, the result list, which contains the island count after each operation, is returned as the output. Here, we start implementing the solution by defining the numberislands2 method. This method takes the grid dimensions, m and n, and a list of positions where land is added step by step. We initialize 2 arrays, roots and ranks, both of size m*n. The roots array tracks the root of each cell, and the ranks array helps optimize the union operation. Initially, all cells are marked as water with -1, and their ranks are set to 0. We also define a count variable to track the number of islands and a result list to store the number of islands after each operation. Next, for each land addition and positions, we convert the grid coordinates x and y into a one-dimensional index. If the cell is already land, we skip further processing and append the current count to the result. Otherwise, we mark the cell as land by setting its root to itself and increment the island count. Then, we define the 4 possible directions to check neighboring cells and prepare to evaluate connectivity. Now, for each neighboring cell, we calculate its coordinates and index. If the neighbor is within bounds and already part of the land, we check whether it belongs to the same island by comparing their roots using the find function. If they are not already connected, we merge the 2 islands using the union function and decrease the island count since 2 separate islands have now merged into one. After processing all neighboring cells, we append the updated island count to the result list. The find function is implemented recursively with path compression to optimize the process of finding the root of a given cell. This ensures that future queries for the same cell can be resolved in constant time by directly linking the cell to its root. The union function, which we use to merge 2 sets, is defined next. The union function takes 2 cells and connects their respective root nodes. It starts by finding the roots of both cells. If the roots are different, it compares their ranks to determine which tree should become the parent. The root with the higher rank becomes the parent, ensuring the resulting tree remains balanced. If the ranks are equal, one root arbitrarily becomes the parent, and its rank is increment to reflect the increased height of the tree. This rank-based merging, combined with path compression and the find function, ensures that the union find operations are nearly constant time. With these helper methods in place, the solution efficiently processes each land addition and returns the number of islands after every operation. In this problem, we are tasked with determining the number of islands in a grid after sequentially adding land at various positions. Initially, the entire grid is filled with water, and each new position represents a cell where water is turned into land. An island is defined as one or more connected land cells, either horizontally or vertically. To solve this efficiently, we use the union find data structure, also known as disjoint set union, which helps us dynamically track connected components. By merging components as new land is added, we can efficiently determine the current count of islands at each step. Let's explore an example to understand this process. Imagine a 3x3 grid where we add land at 5 positions: 0, 0, 0, 1, 1, 2, 2, 1, and 1, 1. Initially, the grid is represented by a roots array, where all values are -1, indicating water. We also maintain a ranks array to track the depth of trees in the union find structure, and a count variable to store the current number of islands, which starts at 0. Now, when we add land at position 0, 0, it corresponds to index 0 in the one-dimensional roots array. We mark this as land by setting roots 0 equals 0 and increment the island count to 1. Since all neighboring cells are still water, no merging is required, and the result after this step is 1. Next, we add land at position 0, 1, which corresponds to index 1. Again, we mark this as land by setting roots 1 equals 1 and increment the island count to 2. However, position 0, 0 is now land, so we perform a union operation to merge these two components. Using the find function, we determine that the roots of indices 0 and 1 are 0 and 1, respectively. We merge the trees by setting roots 1 equals 0 to unify the components and increase the rank of the root at index 0. This reduces the island count back to 1. The result after this step is 1, 1. When we add land at position 1, 2, it maps to index 5 in the roots array. We mark this as land by setting roots 5 equals 5 and increment the count to 2. Since all its neighbors remain water, no merging is needed, and the result is 1, 1, 2. Next, adding land at position 2, 1 corresponds to index 7. We update roots 7 equals 7 and increase the count to 3. Again, all its neighbors are water, so no unions occur, and the result becomes 1, 1, 2, 3. Finally, adding land at position 1, 1 maps to index 4. We mark it as land by setting roots 4 equals 4 and increment the count to 4. However, positions 0, 1, and 2, 1 are already land, so we union these components. After merging all connected components, the island count reduces to 1. The final result for this sequence of operations is 1, 1, 2, 3, 1. In a smaller grid, let's consider a 2x2 grid where we add land at positions 0, 0, 0, 1, 1, 0, and 1, 1. First, adding land at 0, 0 maps to index 0. We set roots 0 equals 0 and increment the count to 1. The result after this step is 1. Then, adding land at 0, 1 corresponds to index 1. We mark this as land by updating roots 1 equals 1 and increasing the count to 2. Since 0, 0 is land, we perform a union operation to connect these components, reducing the count back to 1. The result becomes 1, 1. Next, adding land at 1, 0 maps to index 2. We mark this as land by setting roots 2 equals 2 and increment the count to 2. Position 0, 0 is land, so we perform a union operation, reducing the count to 1. The result is 1, 1, 1. Finally, adding land at 1, 1 corresponds to index 3. We set roots 3 equals 3 and increment the count to 2. Both 1, 0 and 0, 1 are land, so we merge all components, reducing the count back to 1. The final result for this sequence is 1, 1, 1, 1. This example highlights how Union Find provides an efficient way to dynamically track and merge connected components. By leveraging path compression and rank optimization, we ensure that each find and union operation runs in near constant time, making this approach highly scalable for larger grids. To analyze the time complexity of our solution, we start by breaking down the different operations involved. First, during the initialization phase, we create two arrays, roots and ranks, each with a size proportional to the total number of cells in the grid, which is m*n. This step takes m*n time. Next, we process the list of positions, where k represents the number of positions provided. For each position, we utilize the find operation, which uses path compression to optimize the structure of the union find data. Thanks to this optimization, the amortized time complexity of each find operation is O, alpha, n, where alpha is the inverse Ackermann function and n is the total number of cells in the grid, or m*n. Similarly, the union operation, which merges two sets, is also optimized using the find operation and has the same amortized complexity of O, alpha, n. For each position being processed, the algorithm also checks its four potential neighbors up, down, left, and right. This step involves a constant amount of work, or O1, since we are simply determining adjacency. By combining these steps, the dominant factor in the time complexity per position is the find and union operations, each of which is O, alpha, n. When we multiply this by the total number of positions k, the overall time complexity of processing all positions becomes O, k** alpha, m*n. This efficient scaling is key to handling large grids or numerous position updates effectively. Now, let's consider the space complexity of the solution. The main contributors to space usage are the roots and ranks arrays. The roots array keeps track of the parent or representative element for each cell, while the ranks array stores the rank or depth of the tree representing each set. Both arrays are proportional in size to the total number of cells in the grid, or O(m*n). Additionally, the result list stores the number of islands after processing each position, requiring k space, where k is the number of positions. Combining these, the total space complexity of the solution is O(m*n plus k, which is manageable even for larger grids and position lists. When analyzing the best, average, and worst-case scenarios, we observe interesting characteristics of the union-find approach. In the best-case scenario, all positions are isolated, meaning no union operations are needed. Here, the time complexity simplifies to k, as only basic operations are performed for each position. For the average case with randomly distributed positions, some union and path compression operations are carried out, leading to a time complexity of k*alpha m*n. Even in the worst-case scenario, where positions are densely packed and unions occur frequently, the amortized efficiency of the union-find operations ensures that the time complexity remains k*alpha m*n. This demonstrates the robustness of the algorithm across different input distributions. It's useful to compare this optimized approach with a naive brute force alternative. In a brute force method, we would recalculate the number of islands after processing each position by performing a breadth-first or depth-first search on the entire grid. This approach results in a time complexity of k*m*n, as we would traverse the entire grid for every position, and a space complexity of m*n for the visited array used during traversal. In contrast, the current solution using the union-find data structure is significantly more efficient. Its time complexity of k*alpha m*n is far superior, particularly for large grids, since the alpha n function grows extremely slowly. The space complexity of m*n plus k is also comparable or better, making this optimized approach highly practical. The efficiency of the union-find data structure stems from its mathematical properties. By employing path compression and union by rank, each find or union operation achieves an amortized time complexity of alpha n, where alpha is the inverse Ackermann function. This function grows slower than any logarithmic function, making it almost constant for practical input sizes. Consequently, the overall time complexity of k*alpha m*n is nearly linear in real-world scenarios, even for large grids or numerous position updates. This is a substantial improvement over the brute force approach, which recalculates the island count for the entire grid after each position. The combination of theoretical guarantees and practical performance makes the union-find approach an elegant and powerful solution to the problem. When tackling this problem, there are a few common mistakes to watch out for. First, an incorrect implementation of the union-find data structure is a frequent pitfall. Specifically, forgetting to include path compression and union by rank can lead to highly inefficient operations. Without these optimizations, the time complexity can degrade significantly, especially for larger grids. Next, overlooking edge cases is another issue. For example, when the grid is empty or the positions list contains duplicate entries, your solution might fail. Adding the same land cell multiple times should not increment the island count, so sanitizing the input to handle duplicates is critical. Another mistake involves inefficiently checking for islands. Some solutions resort to brute forcing the entire grid after each land addition, resulting in m*n*k complexity, which is impractical for large grids. Instead, focus on dynamically updating connectivity as you process new land cells. Additionally, mismanaging grid boundaries is a common source of errors. When performing union operations, you must validate that neighboring cells are within the grid to avoid index out-of-bounds errors. Lastly, initializing the union-find structure for all grid cells, even those that will never become land, is a waste of memory. It's better to initialize union-find dynamically as each new land cell is added to the grid. Now, let's talk about some insights that are particularly useful in interview settings. This problem is a classic example of testing your understanding of dynamic connectivity, which makes it a popular choice for assessing union-find expertise. Interviewers often look for your ability to optimize grid-based problems by reducing unnecessary computations. While union find is the most efficient approach for this problem, it's also beneficial to briefly discuss alternative methods like DFS or BFS. Although these approaches are less optimal for this dynamic problem, they showcase your versatility and broader problem-solving skills. Scalability is another critical topic. Be ready to explain how your solution performs with larger grids, where dimensions can scale up to 10,000 by 10,000. Here, it's vital to highlight how you've optimized for both time and space complexity. Finally, interviewers may explore follow-up questions, such as handling additional constraints like weighted islands or dynamically finding the largest island. These extensions test your ability to adapt your solution to new requirements while maintaining efficiency. To deepen your understanding, it's helpful to explore related problems. For instance, LeetCode 200, number of islands, is a static version of this problem where the grid is fixed, and the goal is to count islands. Another example is LeetCode 323, number of connected components in an undirected graph, which also leverages union find for dynamic connectivity, but in a graph context. Similarly, LeetCode 547, number of provinces, applies union find to graph connectivity within an adjacency matrix. Lastly, LeetCode 684, redundant connection, uses union find to detect cycles in a graph. When considering alternative approaches, DFS and BFS are intuitive choices for static grid problems but are inefficient for this dynamic version, as they require recalculating connectivity from scratch with each land addition. These methods operate at a complexity of O(k*m*n), which doesn't scale well. On the other hand, union find is the optimal approach here, especially when enhanced with path compression and union by rank, achieving a complexity of O(k*(m*n), where alpha is the inverse Ackermann function. Another technique is grid marking, which involves marking visited cells directly on the grid. While this can save space, it's less flexible for dynamic problems and is better suited for static scenarios. By understanding these variations, you can tailor your approach to fit both the problem requirements and interviewer expectations. Great job! We've covered the dynamic problem of tracking islands using efficient algorithms like union find. Remember, tackling problems like this sharpens your problem-solving skills and prepares you for real-world challenges. Thanks for watching, and see you next time. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!